Hi, Noel scientists. Miss Rose here. Welcome to chemistry. I'm so excited you're here. I love chemistry. It was my favorite subject in high school, my favorite subject in college, my favorite subject in medical school, and my favorite subject to teach. So I'm eager to get started. Woohoo! The reason I love chemistry so much is because chemistry is life. From the clothes you wear to the foods you eat to the oxygen you breathe, which is produced by photosynthesis, a chemical reaction in which plants take in carbon dioxide and release oxygen. Life is all chemistry. Cutting onions, why do they make you cry? Because of a gas that's produced. Why do you fall in love? A lot of it is mediated by hormones and the chemistry in your body. I'm going to share my screen and I'm going to go to Summit Learning, okay? And my page in Summit looks a bit different than yours because I have the teacher-facing page, but nevertheless, we're all going to be working off the same project. It's called NLA Adopt a Molecule. And I love to start off with this project because basically it asks these big questions. How does chemistry affect life? And how does the structure of a chemical affect its function? Now, we all know that there are a huge variety of chemicals we use every single day, from cleaning products to foods we eat to clothes we wear. We're just talking about that stuff. And the way we know a property that a chemical compound has is to look at its structure, and we break that structure all the way down to the atom and even smaller than the atom in the subatomic particles. So what we're going to do in this particular project is we're going to end up picking a compound, anything, caffeine, biodiesel, anything that vitamin D, vitamin C, tryptophan, Vicodin, anything. And we're going to really break it down to what are the elements that make up that compound and what are the uses and dangers of that compound. What are the benefits to humankind and to our environment and to human life? And what are the dangers? And then you're going to present this, and you're going to be able to use a number of different mediums. You're going to be able to do storyboard, Zoom, Powtoon, Flipgrid, recording yourself on PowerPoint, however you see fit. And the cognitive skills that we're going to be working on here are, of course, modeling, oral presentation, and communicating accurately and precisely, which is really important in science. So let's get started. There are also two focus areas, atomic structure and periodic table. So the very first checkpoint you'll notice here is called Atoms and Molecules, and it's due September 18th, which is this Friday. If you click on it, you're going to see the link into the checkpoint, and then everything you need to complete this checkpoint is going to be in this document, okay? And here you have it. It's a great reminder that I'm Dr. Rosemary Miner. Most students call me Miss Rose. Here's my phone number. Here's my email. Please reach out to me. I am here to help. I have the following office hours. As you can see, it's every single day of the week. If you can't meet me before 4 o'clock, text me. I'll meet you after 4 o'clock. If you need help on the weekends, text me. I'll help you on the weekends. This class will meet 3 times in Zoom live. Everyone who takes chemistry will be in my Zoom room and we'll be working on our final products. The first one is going to be September 24th at 11 a.m. The second one is October 8th, which is my oldest son's 27th birthday, at 11 a.m. And the third one is October 22nd at 11 a.m. It's going to be in my Zoom room. I've provided the link, and there's a code to use, okay? So now we're going to scroll down. Every week when you get a checkpoint, it'll be in this same format. These are the materials for the week of September 14th to the 18th, this very week. This is checkpoint number 1. It's due on September 18th, which is Friday. And to really get started, you're going to scroll down to activity 1 and click on the link to the video, okay? And I've also bookmarked it here for you. Oopsie daisy. I don't know, that's not going well. So let's not, oh, there's the bookmark. Click on the bookmark, and here's where you click on the video, okay? But before we get down to that first activity, here's a review of the cognitive skills that we will be assessing on this checkpoint: modeling and communicating accurately and precisely. This is the vocabulary that we're going to be going over during this checkpoint. And here are some resources, readings and videos that may help you complete activities 1 and 2 in checkpoint 1. Several of these I use later on in the checkpoint, but feel free to use any of these at any point. Finally, without further ado, checkpoint activity number 1, okay? So here it is. This is due September 15th. Click here, and this is the video that you're watching right now, okay? And what we're going to do is complete this chart, and then we're going to choose 2 elements from the first 20 elements in the periodic table, and we're going to create a Flipgrid video answering the following questions, okay? There we go. And here's the Flipgrid video. You sign in using Google and your Gmail account, and these are the questions you're going to answer, okay? Very simple. For activity 2, which is due on the 17th, you're going to click on this video, and that's going to provide you with more information about the periodic table, and you're going to complete the glossary above. You're going to complete a definition for all of the vocabulary words here, okay? And if you have any trouble or need some support doing that, there's a glossary I've provided, okay? And I'm going to click on that glossary so you can take a look at it. And here it is. And I've started to fill in some of it, okay? Also, here is the checkpoint itself. This checkpoint is due on September 18th, and it's asking you to write a paragraph of 5 to 8 sentences long describing the history of the periodic table. And here's a short video that will help you. Here are some sentence starters you might like to use as a guide. And then here's where you write your 5 to 8 sentence paragraph. Friendly reminder, don't forget about capital letters and punctuation. That's part of communicating accurately and precisely, okay? So let's go back now that you have a general idea of what your checkpoints will look like every week, what your project is for this quarter, and how the checkpoints will be laid out, where to begin, okay? So here we are, okay? Activity number 1. I would like for us to watch 2 videos together where we will begin to answer the question, what is an atom and what are atoms made of?
What is an atom and how do we know? Atoms are the fundamental building blocks of chemistry. Just like baked goods are made of a collection of different types of ingredients, matter itself is made of a collection of different types of atoms. Scientists have discovered 118 kinds of atoms, which we call elements. You can find them laid out on a chart called the periodic table. All things from the screen this video is displayed on to the eyeballs with which you're watching it are made of atoms. But a single atom is so small, it is impossible to see with the naked eye. So there you have it. A random voice from a video you found on the internet claims that everything is made from invisibly small atoms. You may now blindly accept this as fact and happily move on with your day, right? No? Now you are extra curious? You want to know for yourself exactly why it is that scientists think they know that atoms exist? Well, to find out, we must travel back in time to ancient Greece. Meet Democritus. the man that many historians credit for first clearly proposing the idea of an atom. In his day, it was thought by some that if you were to chop up a piece of matter, an apple for instance, you could just keep on chopping forever and ever. There was no end to smallness. For reasons not fully agreed upon by historians, this concept did not sit well with Democritus. Instead, he insisted that at some point, you would reach particles so small and so indestructible they could not be divided any further. He called them atomos, or atoms, which means uncuttable. Now, Democritus didn't actually have any evidence to back up his claim, and because of that, many people simply rejected it. After all, that which can be asserted without evidence can also be dismissed without evidence. Let's fast forward several hundred years and hop on over to the Arabic world. You probably know that salt can be extracted from seawater by simply letting it evaporate or boiling it dry. People have been doing this forever, but alchemist Jabir ibn Hayyan and those that followed his work took the science of extraction to a whole new level. Through careful experimentation, they developed complex processes of filtration, boiling, vapor collection, and cooling. They found that crude starting materials could be divided into multiple incredibly pure substances. Pure meaning they appeared to be consistent all the way through, unlike the complex mixtures of matter often found in nature. In the 1700s, a French husband and wife scientific duo, Marianne Poltz and Antoine Lavoisier, studied and built upon the work of their Arabic predecessors. They found that certain pure substances could be broken down even further through chemical reactions. Water, for example, can be boiled into steam, which is still water, but it can also be split into two pure gases, hydrogen and oxygen. No matter how hard the couple tried, however, they could not reduce oxygen or hydrogen into simpler gases. They concluded that the gases must be elements, foundational substances that cannot be created by mixing other chemicals together and cannot be broken down any further. With this concept in mind, scientists everywhere began searching for and listing as many elements as they could, eventually discovering all 118 listed on the modern periodic table. Some, such as oxygen and hydrogen, are gases at room temperature. Others are solids, such as elemental carbon and gold. Others still are liquid at room temperature, mercury and bromine. It was also found that under the right conditions, pressure and temperature, certain elements will react with each other upon mixing to form new substances with new properties. These are called compounds. The elements oxygen and iron can react to form a brown powder known as rust. Oxygen and mercury react to form a toxic orange powder. Oxygen and hydrogen react to form a clear, refreshing liquid. You probably know it as water. Though the steps may be complicated, all of these reactions can be reversed. Elements can be re-separated, and the amount of each element we get back after separation is always exactly equal to the amount that had reacted to form the compound in the first place. Wonderful. Elements are real, and they appear to be essentially indestructible, but what are they made of? If you were to zoom in on one, a chunk of pure gold, for example, can you just keep zooming in forever and ever, seeing nothing but pure gold for infinity? In the early 1800s, a school teacher from England named John Dalton grew fascinated with chemistry. Along with conducting several experiments of his own, he read about every experiment he possibly could, paying special attention to the quantities of each element used up in every chemical reaction. In these numbers, he was surprised to find a pattern emerge. When two elements can react to form multiple types of compounds, they always do so in small, whole number ratios. In this example here, we see that in order to transform a gram of carbon into pure carbon monoxide, we need to add 1.33 grams of oxygen. To turn a gram of carbon into pure carbon dioxide, we need to add exactly twice as much oxygen. That's 2.66 grams. This and many other similar observations strongly suggest that oxygen and other elements are made of tiny, indivisible units, atoms. He didn't know exactly how small an atom was, but the numbers suggested that the atoms of a single element were all nearly identical in size to each other, but different in size to the atoms found in other elements. In 1808, he wrote a 560-page book that briefly mentioned his discovery. It even came with some quite beautiful drawings. While scientists weren't fully convinced that atoms were real, they did find the concept of atoms extremely useful. It helped them make accurate predictions and perform cleaner chemical reactions. In 1905, Albert Einstein, hold on there, in 1905 he was quite a bit younger than that. There we go. In 1905, Albert Einstein proposed an experiment and produced an equation that could be used not only to confirm the existence of atoms, but to determine exactly how big they are. A few years later, French physicist Jean Perrin, or I guess in French that would be something a little more like Jean Perrin, used Einstein's concept to actually do the experiments confirming beyond reasonable doubt, at least to other physicists and mathematicians, that atoms do, in fact, exist. Now, if you happen to love math and possess an in-depth understanding of physics, then great. You can just turn off this video right now and go read his book. But for the rest of us, a little visual confirmation that atoms actually do exist would be nice, right? Unfortunately, individual atoms are far too small to be seen with normal light. The wavelength of light is just too great. This means that normal microscopes cannot see atoms. In the 70s, a group of engineers led by Gerd Bennig and Heinrich Rohrer began working on what they called the scanning tunneling microscope, a microscope they hoped would let us take undistorted images of many different types of atoms. It uses a process called electron tunneling to scan and essentially feel the surface of the sample, much like you can feel around in the dark to get a picture of your surroundings. This is an actual scan of silicon atoms forming the surface of a crystal. The colors here are artificial, but this is real data showing the actual pattern of silicon atoms arranged in the sample. Later work by Dr. Wilson Ho improved the technique and cleaned up the presentation of data. While, quote, feeling the atoms does give us good information, researchers still wanted more. A group led by Dr. Ara Apkarian of the National Science Foundation's Castle Research Center discovered a way to use actual light to see atoms. In the past, this was thought to be impossible because the wavelength of light is so much larger than an atom, but by shooting light at the tip of a probe in a modified scanning tunneling microscope, they were able to essentially shrink the light's wavelength and get it to scatter off the sample onto a detection screen. By moving the sample bit by bit, hitting it with light again each time, they were able to piece together this image of a single nitrogen atom, each pixel representing an individual data point from the scan. If we smooth it out, sharpen the edges, and change their chosen color scheme, it is shocking to find how close John Dalton's old drawings actually were to reality. Our species has finally done it. Over 2,000 years after Democritus first proposed the idea of an atom, we have now received direct visual confirmation. Atoms exist. So in summary, what is an atom? Atoms are the fundamental building blocks of chemistry. How do we know they exist? Through chemical reactions, we can witness their effects. Through mathematical equations combined with indirect observations, we can calculate their various sizes. And finally, with the aid of new technologies such as the scanning tunneling microscope, atoms can now be seen. While the word atom technically means uncuttable, we'll see in the next animation that atoms actually can be split apart. Atoms themselves are made of smaller pieces. I'm John Perry, and that's how we know that atoms exist, stated clearly.
Okay, we're going to watch one more video, which is much shorter this time, called What Are Atoms Made Of? And then we'll be able to begin
Stated
work
Clearly presents
on our activity.
What are atoms made of? As we learned in the last animation, the word atom means uncuttable, and when John Dalton first discovered evidence that atoms exist, he gave them that name because he genuinely thought that they were uncuttable. He thought they were fundamental particles, the smallest bits of matter that exist. Well, it turns out that he was wrong. Atoms can be split apart. They are made of subatomic particles, most importantly, electrons, protons, and neutrons. Protons and neutrons appear to be made of smaller particles still, and truth be told, We don't know for sure if there really is an end to smallness. Reality might just keep going on forever and ever the further you zoom in. So, there's something strange to think about. This image was made of data collected from an actual scan of a single nitrogen atom fixed to a metal surface. What we're actually seeing here is the outside of what is called the electron cloud, the outer edges of the atom. The colors here are artificial, but this is the real shape of a nitrogen atom. Here to the right, we see a simplified model of the same nitrogen atom. This type of model is called the Bohr model, named after the physicist Niels Bohr. Other models do exist which are more accurate, but when first being introduced to chemistry, the Bohr model is the easiest to make sense of, and so it's what we will be using here. In the center of a nitrogen atom, we have the nucleus. Looking over at the scan, you might think that the red section is the nucleus. That's actually not the case. As mentioned, the colors here are artificial. The red pixels are just the part of the electron cloud that's closest to us. The nucleus is hiding underneath the electrons. It is the core of the atom. And in our model, the nucleus has been dramatically enlarged so that we can actually see it. If the model were actually drawn more to scale, the entire nucleus would be smaller than a single pixel on your screen. In fact, if we were to enlarge the atom to the size of a professional soccer field, well, actually the size of 10 professional soccer fields, the nucleus would be about the size of a house spider. The nucleus consists of one or more protons, and in most atoms, a collection of neutrons. Protons and neutrons are what give the atom most of its weight, or its mass, technically. For example, a gold atom has 79 protons and typically 118 neutrons. This is far heavier than a nitrogen atom, which only has 7 protons and usually 7 neutrons. The number of neutrons in a particular type of atom might vary between individuals. For example, while most nitrogen atoms have 7 neutrons, some have just 6, while others have 8. Changing the number of neutrons inside of an atom won't really do much to change its chemical properties. Instead, it will often just make the atom slightly heavier, slightly lighter, or sometimes it will make the atom unstable. On the other hand, if you were to add or subtract just a single proton from nitrogen, assuming you had the technology to do so, you would completely change its chemical properties. So much, in fact, that we would no longer call it nitrogen. Adding just a single proton to a nitrogen atom would transform it into an oxygen atom. Taking a proton away from nitrogen would transform it into carbon. In other words, the number of protons an atom contains determines the type of atom it is. When you look at the periodic table, you find that each element has a number. Hydrogen is number 1, nitrogen is number 7, gold is number 79. This number tells you how many protons a single atom of that element contains. Protons are positively charged, neutrons are neutral. Obviously, they don't actually have little faces on them, but it helps to remember. Electrons, on the other hand, are negatively charged. We often depict them as little particles in orbit around the nucleus, similar to planets orbiting a sun, but this is not technically accurate. Scientists tell us that electrons can be best described as wave functions, cloud-like structures that sort of resemble the energy force fields you might find in a science fiction movie. That said, for our purposes today, the simplified model actually works best. In general, the number of electrons an atom contains is equal to the number of protons in its nucleus. This is because each positively charged proton attracts one negatively charged electron. Through chemical reactions, however, an electron can sometimes be stripped away from an atom, or an extra electron can sometimes be added. In these cases, we call the modified atom an ion. Okay, that was a lot of information thrown at you in a very short amount of time, so let's just recap here and summarize the most important bits. What exactly are atoms made of? In the center of an atom, we find one or more protons, and in most cases, we also find neutrons. Protons are positively charged, neutrons are neutral. The number of protons an atom contains determine the type of atom it is. Hydrogen has 1 proton, nitrogen has 7, gold has 79, and so on. Orbiting about the nucleus, we find negatively charged electrons. In general, the number of electrons an atom contains is equal to the number of protons in its nucleus. This is because each positively charged proton attracts one negatively charged electron. I am John Perry, and that was a basic overview of the anatomy of an atom stated clearly.
Okay. So I'm going to return now to our activity. In here, I'm going to ask you to fill out this chart for your activity today and to videotape yourself on Flipgrid. But first, I want us to look at a few more things. Let's take a look and review what we've learned. The elements that you find on the periodic table are made up of atoms. For instance, carbon is an element on the periodic table that is made up of carbon atoms. And here we see a carbon atom. This number 6 is what we call the atomic number. And what the atomic number tells us is the number of protons in the nucleus. Protons are positive. And so inside of this nucleus are 6 protons. If we have 6 protons, we have to have 6 electrons. We have the same number of positive charge protons as we do negative charge electrons. But the electrons are not found in the dense, heavy nucleus. They're found orbiting the nucleus in electron shells or orbits. This very first shell can contain only 2 electrons. So 1, 2. The very next shell can contain 8. We need 4 more. We place north, south, east, west. And so now we have 6 protons in our nucleus and 6 electrons orbiting, 2 in the first shell and then up to 8 in every other shell. Now, we cannot change this number of protons. If we do, we change this atom from carbon to something else. This atomic number tells us the number of protons in the nucleus, and it also tells us that this is a carbon atom. The number of protons tells us it's carbon. If it's carbon, it has 6 protons. If it has 6 protons, it's carbon. If it doesn't have 6 protons, it's not carbon. So now we've gone over 3 of the subatomic particles that you've learned today. We've gone over protons and electrons, but we know that neutrons are also in this nucleus with protons. So we go down here to something we call the atomic weight or atomic mass. And here it's 12.011. And we round this atomic mass to the nearest whole number. So we see that the nearest whole number to this is 12. If the number following the decimal point is 5 or greater, this would go up to 13. But since 0 is not 5 or greater, we stay with 12. So now we take this rounded atomic weight or mass and subtract from it 12, the atomic number 6. 12 minus 6 is 6, and that is our number of neutrons. So we place 6 neutrons in the nucleus, okay? Now, I want to take a minute to use a function here called the whiteboard, okay? I want to now take a look at drawing another atom, just to give you an idea, okay? So I'm going to go to, let's see if I can go to, I'm going to stop sharing that, and I'm going to go to my handy dandy periodic table, which you have a copy of in all of your links there, okay? I particularly like this periodic table because, as you see, as I click on something, I can get that to come, okay? Phosphorus, nitrogen, oxygen, fluorine, beryllium, okay? So let's do beryllium. Beryllium has 4 protons. Its atomic number is 4, and its atomic mass is 9.0122. 9.0122. So now let's return to our screen and our whiteboard, and let's draw beryllium. Okay, let's not forget that beryllium is Be. And let's remember that its atomic number, this is a lot harder than it looks, guys. This is basically atomic number. Does anybody remember? Uh-oh, that wasn't good. Let's go to text. No, let's not. Let's go back to draw. Atomic number was 4. That's that small number, the smaller number on the periodic table. Its atomic weight or mass, either word suffices. We can use either. So let me use atomic mass because it's easier to spell here. Okay. It was, I think, 9 point 0.0122. Okay, here we go. I am going to now begin to draw this beryllium atom. I start with a circle. I know its atomic number is 4, so I know I have 4 protons. And I put a little p here. And I want you to remember that protons are found in the nucleus, as you can see right here in this nucleus, and they're positive, okay? If I have 4 protons, 4 positive charges, I'm going to have 4 negative charges. Those are called electrons, okay? Oh, this is really quite something. And they are negatively charged. They go in orbits or rings around. We know that the first ring can only have 2 electrons. The first ring can have 2. So I put the 2 in. And this is the way you draw them: north, south, east, west. Okay. But we know that we only have north and south in the first ring because we can only fit 2 electrons in the first ring. But we said we're supposed to have 4 electrons. We have 4 protons because that is the atomic number. So we have to have 4 electrons. I've got 2 in the first ring. I'm gonna need another ring. So let me draw that other ring right around here. and I need to put 2 more. Again, I begin north, south. Now I have my 4 electrons. I could fit 6 more here. Of course, I don't need to, but if I needed to, I could. Now the question is, so this is something we call the electron cloud. And this is where electrons are kept. They are in orbits or orbitals around the nucleus in what is known as the electron cloud. Okay? So there we have it in the electron, I keep clicking onto this, electron cloud. Okay? So now, guys, I have most of what I need. I have drawn my nucleus, which I'm going to label now. So you can see I have drawn my electron orbits. Okay? I have drawn my protons and my electrons, but now I need my neutrons. If you remember, neutrons are neutral. They do not have a charge. That's why they're called neutrons. So we have no charge. So I'm going to call them 0 charge. But how many do I have? Well, I'm going to have to look at this atomic mass. I'm going to take this number and round it to the nearest whole number. 9.0122. I go to the decimal point and look at this digit. If it's 5 or greater, this becomes 10. If it's less than 5, it stays 9. So the answer is 9. Now I subtract from this number my number of protons, which here is 4. And so there we have it. So the answer is 5. I have 5 neutrons. So now I go back to my nucleus because neutrons are also, and I do 5 neutrons. And this here is a beryllium, oopsie, atom. Any questions on that? I'm going to do one more for you. I'm going to do fluorine. Perhaps you've heard of fluorine. It's inside toothpaste and it protects your teeth from cavities and decay. So let's do fluorine. So I'm going to erase this entire board and let's do fluorine. Okay? Whoopsie. Let's click eraser. And this is the best. Just all of my hard work is gone. Okay. Now, if this is confusing, it's going to get easier and easier as you do it. Okay. So I'm going to remove this. And I'm going to look at my periodic table. And this is where everything starts. I've got to go to my periodic table and I've got to look at fluorine. Here's fluorine. Fluorine has 9. Fluorine. Fluorine is 9 protons. Its atomic number is 9. Its atomic mass is 18.998, and it's fluorine, and its symbol is F. Okay, fluorine. Here we go, fluorine. Not to be confused with chlorine, but they are in the same family, and chlorine we put in pools to keep out bacteria. All right, I'm going to write this down so that I don't forget. 9 and 18.998. Let's return to our whiteboard. We are talking now about fluorine, F. We know that its atomic number is 9 and that its atomic mass is 18. Oopsie. 0.998. 9, 8. These are tough numbers to make. Okay, let's begin by drawing the nucleus of this atom. Okay, I know right away that there are 9 protons in this nucleus. I know that because the atomic number tells me the number of protons. Protons are positive. They're located in the nucleus, okay? If I have 9 protons, then I have to have 9 electrons. These are positive. Let's keep in mind. So I'm going to go around and add these electron orbits, okay? I know the first shell has 2 electrons. I need 9 of them. So I'm going to do 2. Now I need a second shell. And because I need to have 9, I need to have the same number of positive protons as I have negative electrons. So let's see. Remember I told you we're going to do north, south, east, and west. All right, how many electrons do I have now? 1, 2, 3, 4, 5, 6. But I need 9, so back to the north. 7, down to the south. 8, off to the east. 9. There we are. I have 9 electrons. Now I need to figure out how many, so 9 protons, 9 electrons, which carry a negative charge, and how many neutrons. Okay, let's put this in here so we don't. Okay. Protons are found in our nucleus, right? Electrons are found in the electron cloud, and neutrons are also found in our nucleus. How do we calculate the number of neutrons? We go to our mass, which is here. We round to the nearest whole number. We go to the decimal point. We look at the number after the decimal point. If it's 5 or greater, we round up. 9 is greater than 5. So we're rounding up. So we're going to do 19 instead of 18. This is closer to 19. And we're going to subtract this top number, or our atomic number, minus 9. And we are going to find that an atom, of fluorine has 10 neutrons, okay? And I've just drawn an atom of fluorine. And every single atom of fluorine looks exactly like this atom of fluorine, okay? Now, there's a couple things I want to really drive home. Protons, atomic number, tells you the number of protons. Protons tell you the element. If I tell you something has 9 protons, you know it's fluorine. It can't be anything else. It has to be fluorine. Protons tell you the atom, okay? The other thing I want you to know is that the protons and neutrons in the nucleus, okay, are very dense and heavy. They weigh 1 AMU. This is atomic mass unit. This is what protons weigh. And protons are in the nucleus, okay? Neutrons weigh the exact same. This is what a proton weighs. Neutrons also weigh 1 AMU. And this is what neutrons weigh. And protons and neutrons are together in that nucleus. And so that's why the nucleus of an atom is very, very heavy, because that's where all the weight is. Okay? Now, on the other hand, electrons that are buzzing around in this big cloud, imagine those 10 soccer or football fields and this tiny, tiny ant in the middle. The tiny ant in the middle is the nucleus, but it's heavy. It's heavy. Everything around it is just this fluffy, light cotton candy, the electron cloud. The electron cloud weighs nothing. So even though it has a bigger volume, it takes up a bigger space, it's very light. It has no weight. And this is electrons. And so when you go to complete this chart, it is going to be asking you to talk about these three subatomic particles, the particles that make up an atom. And a proton is always positive, P. A neutron is always neutral. And an electron is always negative, okay? We know that protons and neutrons are found here in our nucleus. Yes, and that the nucleus is very heavy compared to the electron cloud. We know the electron cloud is very light, okay? Here is the electron cloud, okay? And the electron cloud has almost no weight because you see here that the electrons have no weight. Protons and neutrons weigh 1 AMU each, okay? That is going to help you complete this chart right here. And then what I want you to do is choose any two elements from the first 20 elements. So you're going to choose any elements you want. We've already drawn fluorine, and carbon's been available, and we've drawn beryllium. You can do lithium, you find in batteries, or sodium, you know that's in table salt, or magnesium, or aluminum, and we've all seen aluminum, or chlorine that we put in pills, or sulfur, or phosphorus, calcium, or potassium. You know we find this in bananas. You can pick any of the first 20, and I want you to tell me the number of protons, neutrons, and electrons. Give me the name, for instance, calcium, and the symbol. The other interesting thing is an interactive periodic table, which I love. This periodic table tells you where do you find these elements. Some of their names you may know, like lithium batteries, but you may know nothing about magnesium or silicon or sulfur. Where do you find them? This is really interesting. Did you know that hydrogen makes up most of the sun and stars? We know there are helium balloons, and we know neon is the stuff that lights up those colorful signs. We know fluorine's in our toothpaste and oxygen is in the air, but did you know that sulfur can be found in eggs, or that argon is in light bulbs, or that fruits and vegetables are loaded with potassium, and that calcium and phosphorus make up your bones? That silicon is found in stone and sand and soil, and it's also found in some artificial breast implants. Truth. Magnesium, very, very important. It's in chlorophyll, which is what gives leaves their green color. And when leaves die and the chlorophyll goes, the green color goes. And that's what's set to happen this fall. We know that sodium is found in salt, but did you know that beryllium is in emeralds, those beautiful green gems? All over the place, we see over and over again in this chart that copper is in our wiring, and nickel is in coins, and iron is part of steel that we make bridges with. And over and over and over again, we see the uses of these elements in the periodic table. In our next video, we'll delve into the discovery of the periodic table, the organization of the periodic table, and learn the difference between a lot of groups of elements. Again, if you have any questions, come and find me. Best of luck. I know you can do this. I have such enormous confidence in you, and I wish I could be there with you face to face, but I know we will be soon. But I know that we can learn chemistry no matter where we are. Thank you.